Okay, thank you for being here this evening. I'm Italian, and you can tell this by the fact that I'm going to move a lot my hands and I'm going to walk up and down. This is because I cannot contain my excitement for this topic. But if you want to contain my excitement, just raise your hand at any point, and I will be happy actually to take any question or comments. Okay, so I'll start by telling you why I'm interested in this, what brought me here. So I'm interested in structure, engineering structure, from satellite to bridges. And when you have this type of structure, they're subject to broadband loading. And that's what they have in common. What they have in common is that we actually use model to describe them. And this model can be a simple 1 degrees of freedom, or it can be a car or a wind turbine type of more detailed model. And what we are looking at are this type of information that we can collect from this structure in operation. We collect data, we collect measurements, but we collect also other type of information. We collect this. We look at inspection report, we look at failure reports of some of this structure. And this actually leads me to think about 3 engineering grand challenges that I'm very passionate about. And these are the following. How can we design better structure, accounting for nonlinearities and uncertainties? How can we actually monitor these structures to assess their remaining useful life? And accounting for the fact that we have also sparse data that we have to deal with. And how can we actually make full leverage of what is machine learning to make explainable and interpretable prediction? Okay, to do so, I established the data vibration and uncertainty group. And what we do there is that we go from the fundamental physics, literally from a lab in which we do very small tests, to actually building the physics-based model, to look at uncertainty quantification and integrating all of this information. And we go all the way through. And I'm going to give you a few examples before starting with the actual talk. Some recent examples include actually what we did with reports and how to extract information from failure reports. And there we were interested in failure of sensors like wearables. And we were looking also how we can leverage information from reports and domain documents to create these knowledge diagrams. We also look at how we can enhance our model by integrating physics and data, and how we can update more effectively this model. And we also look at ways to assess friction. And we also look at maintenance planning. So you can see that they go across very different sort of topics, but they all come together to solve the biggest challenges that we face in engineering nowadays. I'm also interested in cross-disciplinary research, and I've been very lucky to work with the zoology department in Oxford. And this is an example of this research in which we were interested in looking at how vibration is generated via animals and how they communicate, and can we build the most simple model. And very recently, we also look at spider dynamics, because we are interested in understanding how they are sensing, and if we can transfer the knowledge from these animals actually to engineering practice. Okay, that's enough for the introduction. Now I'm going to tell you what I'm going to tell you about in this presentation. I'm going to first talk to you about why do we need something that goes beyond data-driven. And then I'm going to slowly move through what is physics-enhanced machine learning, and which are the challenges that we tackle thanks to this technique, and which are still challenges that are open and opportunities for this type of technique. Again, at any point, please raise your hand. Okay, so I'm talking about machine learning, so I have to start with the sort of usual disclaimer. Machine learning and artificial intelligence are not necessarily the same thing. And actually, with artificial intelligence, we are talking about a computer system that can perform tasks that usually are performed by humans. And with machine learning, instead, we are looking at ways in which we can build algorithms. And what I mean by that is that we have some data, input and output data, and we try to construct algorithms out of that. And these algorithms are specific to solve specific tasks. And some of these tasks that are best solved are about recognizing patterns, like face recognition, recognizing anomalies, and everyone nowadays is very much aware of generating patterns in terms of generating text, and also generating reports, knowledge, and reports. But of course, they can be used also for prediction, and they're actually very, very good at that. And prediction can be in terms of time series forecasting, but again, can be about text. Now, When I'm talking about machine learning, of course, it's very easy to start talking about artificial neural network. And those are just one type of technique, a very popular technique, and I will touch upon it later on. And of course, if you think about it, then there are all the buzzwords about deep learning that are coming in. As you can see in brackets, I was mentioning actually when the research started in those fields, and actually was quite some time ago. But the reason why they're becoming very, very popular nowadays is because of the fact that we have access to graphic GPUs, and we have lots of data, and we also have libraries that are readily available that we can use. So this is very important to remember. These techniques have been developed over a large number of years, and we are taking full advantage now because of these things. Okay, so why so important in engineering? Well, imagine that you have lots of data. Now you have an opportunity to extract and summarize information, learning patterns, but also think about inspiring new experiments to get more information. It's also very important because you can automate repetitive tasks, you can develop actually algorithms, but you can also develop models that are of the reduced order, so they run much faster. And of course, this also brings us to the fact that we can use this information to do online tracking of our structures. Now, this is all great because all of these tools help us today to guiding decision-making. Now, thinking about guiding decision-making, we have to exactly think about what we mean by that and what are the consequences. So I'm going to give you an example. So this is me yesterday writing a WhatsApp text, okay? So I'll start writing today, I will give up, and you will see that there is talk, call, seminar. Okay, that was a good prediction, and of course this is based on my data set. And if I start writing S, you can see something else that is written there. Today I will give a sleep, for example. Now, the reason why this is written this way, as you may notice, is that I'm also using the Italian keyboard and not the English one, so it's getting very much confused. But anyway, even if the prediction or the suggestion that is given to me is wrong, I can fix that, and it's very much low risk. Similarly, if you think about Netflix, one of my favorite movies of all time is actually Memento. But because I've been watching on a certain profile on Netflix, certain type of movies, it's telling me actually that the percentage of match is quite low. Now, again, the fact that it would suggest me that this is not probably the best movie for me is not a problem. I can fix that decision. And in case I'll take the decision to watch it or to watch another movie, it's going to be okay, right? The consequences are very low. But now in engineering, we are talking about structures, systems that will affect human lives and can create, we can, in principle, stop failures if you are able to assess correctly the data. And we can make life better for people, even, for instance, thinking about wearables. In a case, we are using it to monitor the glucose level. And if you think about it, this is also important because we have lots of data to help us guide decision. But now, in engineering, what we are talking about are decisions that have high-risk consequence. So we cannot just rely on the fact that there's going to be a miss in the suggestion or in the person actually being able to understand that there was a problem, because the data set that we are talking about, the information, is much, much bigger. Okay, so I hope that this convinces you why it's so important. It's guiding the decision-making, actually, that makes physics so important. So let me give you another hint why using only data might be problematic. So we have this x and y. So those are two variables for which we collected, actually, some observations. So we collected observation for y. And these observations are noisy because we are collecting that with some sensor. Okay, what we can do is to think about what's the underlying model. Now, if we have only the data and we know nothing, we will not know what to say about this. Now, the underlying correct relationship is actually what is drawn here in this graph. And if we use machine learning, we might get, we might get something that looks like this. So it's not bad, and actually it's a very good approximation of the underlying physics. And the way in which it's been obtained has been by deciding a model and optimizing some of the parameters of this model, like the weights, the biases, and which function, activation function we're going to use. Okay, what does it mean? Well, if we were lucky, depending on the model that we chose and the parameter that we identify, we may get a good fit. But what happens is that we might get also completely a wrong fit, and we can have underfitting models. There is this blue line that goes across. We can also have an overfitting. We can try actually our model to look at every single data and actually pass through almost every single data. Now, this is a problem. And the reason for this is that, of course, we are going to train our model with the training data set. But if we want to use it for something that is slightly different, being overfitting might lead us to a wrong decision making. And the thing that we have to remember all the time is that these models are never going to be perfect. There will always be an error. And this is coming from the fact that we're trying to minimize the error in the training data, and then we're going to assess our performance on test data that weren't seen during training. But not necessarily we're going to have this zero error. So we might get a good fit, a very good fit. But when we will have different data, this might change its performance. Okay, I hope this makes sense so far. I can see people in the audience nodding. That's good. Okay, but what about the physics, right? We might have known this variable y in terms of x, in terms of physics. And maybe this is still the underlying correct relationship is there, but maybe the physics was a very good approximation for this problem. And maybe the physics were describing something very simple as the equation that is written there. But how do we choose this coefficient? How do we know that that was the correct model? And this is bringing back similar question, but now at least we add with physics some physics knowledge that we are embedding. And I'll tell you later how we can embed different levels of physics in models. Now, just to clarify what I'm trying to make sure they come across, when we have a physics-based model, we have an algorithm. We have a relationship between y and x. And what we say is that because of this input data and this relationship, now we get an output data. This is because we have a causal model. There is a causality between the x and the y that we are actually enforcing. Again, when we do machine learning instead, we take the input and the output, and we look for an algorithm that solves a specified task. That's very different, and we have to be careful when we are using machine learning for this reason. Okay, what is the catch-alls in engineering? When we talk about data from texting or from Netflix, of course, that data is actually accurate data. There is no uncertainties in the observation, we can say. However, when we talk about engineering, data is not enough. We should look for information. How this data is actually going to be informative to our task. And informative means, can we actually look from the signal and distinguish things that cause the signal? So, for instance, if we are looking at the vibration of a wind turbine, if the vibration was caused by operating condition, can we distinguish if it was caused also by the environmental condition in that specific time frame? Can we do something about it? And also the question is, what data do we need? What to monitor, where and when? Of course, another assumption that we do all the time without even thinking in engineering is that the data is accurate. This means that the sensor that we are using are low noise, are calibrating, stable. We're also assuming that everything is reliable and that we will observe the served behavior consistently. Now, the main problem that we are facing is that at the end, as I told you, we are saying that the machine learning model is input and output data. We are not enforcing any physics and not any knowledge. So the model will be as good as the data. But now the catch is that in engineering, we cannot observe all the possible conditions from the data. And it's difficult to label those conditions in any case. Data may be very expensive to acquire because maybe, for instance, if we are taking on a bridge, we will have to stop the bridge. Or we will have to find a way to measure in points that are actually usually very difficult to access. And the data can be heterogeneous. It's not just of the same time. It's not just only words, or it's not just only, me selecting type of movies. This information can come from various sensors, like satellite images, like accelerometers, strain gauges. They have different spatial, temporal resolution. But this information can come also from reports, from pictures that have been taken. Okay. The other catch is thinking about the data itself. Is the data up to date? The structure lived for a longer time, and we would like to understand how things evolve with time. But can we trust the data quality? And are we going to basically look into data biases? OK, so if this makes sense to you, now I hope that this figure will help you even to consolidate this type of problems. So let's imagine that we are in a space in which we have physics knowledge on the x-axis, and on the vertical axis, you see the data availability. And again, as I told you, this must be informative data. It's not just that we have data. This data carries some information. OK, we can divide this space in 9 regions. And if we are at the top left corner, in which we have lots of informative data, but we have very little physical knowledge, what we'll use is machine learning. However, if we have very little data, but we have lots of physical knowledge or medium physical knowledge, we will tend to use more physics-based model. Everywhere else, we actually need an hybrid. We need to leverage what we know from physics and what we know from data. Most of the time in engineering, we are actually in these regions. And the reason why this is so important is that the volume of useful information, and again, I'm talking about information, not just data, is actually very little. And if you want to use this model in context that then can be generalized for other applications, as it will be with a physics model, then what you would like to do is actually to enforce this physics knowledge. OK. Now, what it comes next is actually I'm going to tell you about some of the warnings. So with machine learning, if we use data only, we can have poor generalization performance, which means that if we're trying to extrapolate the behavior outside the data set that we have observed, we might get something that is wrong. We might get also results that are completely physically inconsistent and implausible. The main reason, by now, I hope that you can guess, is that this relationship that we might find might be based on corrupted and non-informative observation. And this relationship do not have any of the causality relationship that we discussed earlier unless you enforce it. And we are not distinguishing necessarily from the measurements the different sources. What it means is that we may get very accurate but wrong prediction. OK. Now, physics-based model can be dangerous as well. Why? Because we're going to build a very detailed physics-based model that contains all the physics that we know. And this might take lots of computational cost. But we still might get physically consistent but not plausible prediction. The reason for that is that we're going to make some simplifying assumption, of course. We cannot represent every bit of reality, so there's going to be uncertainties. And of course, this uncertainty comes from the input, from the parameters, from the model itself. OK, so where does this lead us? So this is a very famous quote, and all models are wrong, but some are useful. And indeed, you have to think carefully when you try to use physics or machine learning about what kind of information you have available, and never forget the assumption or where you validated your data set. OK, I'm here to talk about how to integrate data in physics. So why this is so important? Again, it's important because of the high consequence decision that we are making, and the fact that we have to communicate that to humans. This decision must be interpretable and explainable. What I mean by that? We should be able to help someone understand how a prediction was made, which means that if something fails, someone should be able to go and figure out why it failed. And we should be able to communicate this, basically this prediction. What it means communicating is not just it's not just being comprehensible, but actually is quantifying also any remaining uncertainties. And being able to say, this is my prediction, but this is the uncertainties that also it's carried in. Now, interpretability, of course, is related to the fact that the human will trust more prediction in which they have a model that they can interpret, like a physics-based model. Explainability, instead, goes to the fact that we have to present this result to someone, and this someone ultimately is a human. OK, So how does it work if we have a wind turbine, and what are the challenges there? So I'm going to walk you step by step. And again, if you have any question, please raise your hand. I will be very happy to take it. So let's imagine that we have a wind turbine in offshore condition, and we have some input. And this input, again, is the operational condition, but is also the environment. Now, there is going to be a true response. This wind turbine, for instance, is going to start to vibrate. What we do then is to put sensor. Now we are measuring, and we're going to have a Y measured. Now, we can also decide to build a physics-based model. This could be at the design stage or actually later on. And what will happen is that there we will build an input model, and we're going to have also a Y model. Sorry for that. What we can do later on with the measurements is to try to build a model of the measurement, because maybe the data was sparse, was noisy, and we will get something as you see up there in the right corner. And what you will see is that we can call it Y data. But now we can combine physics and measurements, and what we'll get out of it is this Y physics plus data. Well, none of them match the other. They are all very different. And this is actually very interesting, because depending on what you're using, that will determine the prediction and the accuracy that you will actually have with your prediction. Now, why this is the case? Well, let's remove the wind turbine. Let's talk about, in general, of dynamical system. There is this relationship, Fx, that we actually don't know. And what is happening is that we're going to measure, and we're going to have an error in the measurements. And this error is going to be the difference between what we measure and what was the true response. Now, if we have a physics-based model that is approximating part of the physics of the complexity, what we will have, sorry for that, is an approximation of this Fx, a G function, in which we will have some input parameters of the model, and we're going to have some uncertainties also in the parameters, this theta p that you see over there. And we're going to have a physics-based error, because the true response and the model response are going to actually be different. Similarly, if we were to use an approximate data-driven model for the measurements, we will have another approximation. Now we're using a data-driven model, D. Now, with this D, we're going to use the measured X and Y, what we measured, but we're going to have different parameters. Notice that before we have theta p, that was the physics parameters. Now we have theta d, because these are coming from the data-driven model. And we're going to have a data-driven error. And if we combine physics and data, we're going to have the conjunction of the two in whatever way you want to carry that. But now we're going to have a physics data error, and we're going to have multiple parameters that we will have actually to identify correctly. What this brings me, basically, is that we're going to have lots of errors. And this error can be unknown or can be random. What I mean by that is that unknown is calling usually, it's an epistemic uncertainty. It's something that is due to the user not knowing precisely something, but if you can measure it, it will be one value. Aleatoric, instead, is accounting for the actual variability, the fact that no matter what, things will vary. So you better describe this variability, for instance, with a probability density function. Now, we can have also error in the actual model that we built, right? Not just in the parameters. And these are called model discrepancy. What it means is that we can talk about aleatoric and epistemic uncertainties, but also on model discrepancy. And this model discrepancy can be due to the physics, so to the approximation that we are making, but also due to the data. Now, these are sort of what are called known unknowns. We know that we have this uncertainty, we can characterize it. But what if we don't know that uncertainties? What if we have some of the parameters of our model that we cannot characterize because we cannot carry out the experiments or we cannot access their information? What if we don't know that we have the wrong model? Maybe there was some nonlinearity in the system that was very important, but we actually didn't model it. So this is causing actually what is called irreducible uncertainties. And those are very, very challenging when we are actually dealing with models. So what I'm going to try to show you here, again, a 2D graph that I hope that help you understand why it's so important. In this graph, you will see the influence of uncertainties on performance metric versus the access to information that can help us either to reduce the uncertainties or to actually quantify it. And again, we're going to have 9 regions. Now, what we can do is that we can look at the uncertainties, and we can think about when we can actually reduce or quantify, so we have an high access to information, or we can have very low access to information. And so the uncertainty cannot be described. Similarly, we can think, we can think about model and how model can be approximated. Well, if we have very little influence of uncertainties, a model can be considered as deterministic. And then we can have medium or high level of uncertainties. And this can be caused by model, or the parameters of the model, or by the model itself. And depending on the application, the importance, the influence might swap. Now, if we are in this left part of the graph, what you will see there is that basically it doesn't matter if we can quantify really uncertainties. However, most of the time, we are actually in this region there. And what we would like to do is to characterize these uncertainties. If we have partial knowledge, we would like to know how to gather info and what info to gather to actually get better model that can quantify these uncertainties. However, we might be in this bottom part of the graph in which we have these irreducible uncertainties, something that we cannot actually describe appropriately. And what it means is that we are back again into a dangerous zone because we might have very poor model prediction and an underestimation of the actual uncertainties. And again, this leads to very accurate but wrong performance prediction. Very poor inference on future health condition, and at the end of the day, poor decision making. And again, we are talking about critical engineering structures. So it's very important to be able to characterize these uncertainties. Okay, so I hope that this first part helps you understand why it's so important to go beyond data-driven. And this is all related to high-consequence decision and how we use the model. If there are any questions at this point, I might take them in the room. No? Okay. Then I'm going to move to the next part. And I'm going to tell you about what it is this physics-enhanced machine learning and how we are building these hybrid physics and data models. Now, physics come in different forms, or anyway, our physics knowledge come in different forms. It might come from observation, because we have data set or data that can be generated in the lab, in operating condition, or with models that actually embody the underlying physics that we would like our model to actually represent. Another way of thinking of embedding physics is to think about this inductive bias. We know about conservation law, symmetries, boundaries. We would like to embed that. Another way of thinking about embedding physics and domain knowledge is to think about how we can structure our algorithm to help us get there faster. And what it means is what algorithm we should use, which loss function, which optimization. At the end of the day, we are dealing with model, and if we have some physics knowledge, we might put in also, and we might add in some part of the physics knowledge, some of our model. What is the reason to do this? Well, if you have a data-driven model, your space of solution can be so large that by adding these constraints, you're actually getting closer to the true solution. And of course, if you are doing the training, this will speed up the training and will enhance the generalization. And of course, what is interesting is that if you are familiar with neural networks, usually everything will go in the loss function. In this case, it doesn't have to go in the loss function. And I'll give you, again, an example to explain this. Okay, so we are looking at PINS architecture. There is physics-informed neural networks. And what we would like to do is to accelerate the solver. So we have a partial differential equation, a PDE, and what we are doing is generating input and output data through models. Now, what we want to do is to create a data model, a data-driven model, in which basically we create this regression. And what we have to do, basically, is define some of the hidden layers, some of the number of nodes, we have to specify the function, and what we're trying to do is actually train this network for the weights and biases. Now, we are not training the neural network independently. Actually, we are taking into account that we know part of the physics, that we know part of the PDE. And our loss function, in fact, is not just looking at the error between the training data that we have, but we are looking at the output layer, and we are looking at the results of the partial differential equation. What is interesting there is that this loss function can contain information that comes from the boundary condition, the initial condition, but also what is called the residual. And it's actually the actual equation that we know. So what is happening is that if the loss is actually not satisfactory, we might go back and generate more training data, or we can say, okay, no, we are done. Now, what you see here are actually all the biases that I described to you earlier in action. In green, you see observational biases, the fact that we might give inputs to our model that actually embody the underlying physics. We can have what is called inductive biases, that is incorporating prior assumption. And what we can do is also having learning biases, how we construct the neural network architecture and how we choose the loss function. But also we have these discrepancy biases about incorporating the physics. And what happens is that not all of them comes into the loss function, they come everywhere into the architecture. This is just one example, and PINS is one of the most popular physics-informed machine learning technique, or physics-enhanced machine learning technique. I'm very sorry. It seems that sometimes my pointer wants to go ahead faster than me. But now, let's talk about the different ways in which we can start and the different way in which we can build our models. So in engineering, we start by asking the question, how much physics do we have compared to data, right? And how can we integrate that? Now, you can start from a physics-based model, or you can start all the way to a data-driven model, from a data-driven model. What it means is that if you start from the physics and you embed data, you have a physics-guided machine learning. If you start from the data-driven and you go towards the physics, you have a physics-informed, like the PIN structure that I showed you before. Or you can actually come from both sides, and you will have a physics-encoded. Now, very, very little maths to say that if you have a physics-informed, you have a model that is actually your data-driven model, plus some of the biases that we described earlier. If you start dealing with a physics-guided, you have the model that is the G model from before, with some parameters that are physical, the theta p that we saw earlier, and we add biases. And what you can do is also have physics encoded, in which you're combining all of that with the biases. So these are the sort of three types of structures that you can have. And if you're wondering why we are doing all of this, is because we would like to overcome this poor generalization performance. We would like to remove physically inconsistent and implausible prediction. We would like to be able to quantify uncertainties and provide explainable and interpretable, fast and accurate inferences, but also informing physics. But how can we do that? Can we have just a method that will work all the times? And of course, that will be a dream. But first of all, we have to think about which are the information that we have to integrate. And in fact, with physics-enhanced machine learning, as I mentioned to you, this integration challenge goes actually beyond mathematical models and data. I described to you some domain knowledge, some prior knowledge, first principle, some data that can be multi-fidelities and heterogeneous, and also we have always to remember that we might have some physics that we actually embed in the method, but this physics can be wrong. And we're going to deal with data, and as I mentioned to you earlier, data can be corrupted or not informative. And we are dealing with uncertainties, and we are dealing with strategies that we need to validate. Now, this is a big integration challenge that goes well beyond just solving the points that I described in the previous slides. So how can we solve this, and is it applicable to all the system? Well, of course, there is no one-size-fits-all. There is not just one method that can be applied. And it really depends, again, on how much physics you have, data, but also what's your purpose. Why are you using that technique? And what is the complexity of the system? It's something that you always have to keep in mind. I'm going to just give some very small example. But if you have lots of physics and you start adding data, what is called physics-enhanced probabilistic machine learning can be the best way to go forward. And instead, if you are at the other end, you might use a PIN structure, this physics-informed neural network that I just described to you. So sorry. Depending on the purpose, we might decide to accelerate in the solver, as I showed you earlier, but we might decide to identify some unknown terms or developing a time-evolving digital twin. And depending on the complexity of the system, we might deal with linear time invariant system, non-linear time varying system, but also multi-scale, multi-physics. Depending on all of these challenges, we have different ways in which we want to combine the physics and the data, but they can broadly group in those 3 areas that I mentioned to you earlier. Okay, so I hope that this explains to you what is the goal of physics-enhanced machine learning, what are the challenges, and how to combine them in a very high-level way. I'm going to show you now what challenges we were able to solve thanks to this combination. And I'm going to give some examples, and these examples were run actually by Jan, by Joanna, Luca, and Christos. And I'm going to show you also the paper that they've written. So the first challenge that we were dealing with was actually dealing with the real bridge. So we have this Yessel bridge. There is a bridge that is in the Netherlands, and we are monitoring it. And actually, TNO was monitoring this. And we were looking at different positions from H1 to H10, in which we were having strain gauges measurements. And we were doing control loading tests on this bridge. Now, normally, when you have this type of problem, what you do is that you build a physics model, and then you update your knowledge. But you make some assumption. You assume that the data is all data, it doesn't matter, and you update your knowledge. And what it means is that you assume that the data is coming from the same distribution, IID, and you don't care about the results that you will get later. Now, the position of the sensor actually really matters a lot in the accuracy of the results that you will get. And this is just a very simple representation that I hope that will make sense visually. So if you have sensors that are very much far away from each other, you will see no correlation. There's no structure. It looks random, right? The points are all there. But when you start getting closer, those sensors will actually carry the same amount of information. Okay? So the position of the sensor, where the data is coming from, will actually matter. And what we were dealing there is basically we want to identify these physics-based model parameters. But most of the time, what we do is to assume that the data is completely uncorrelated, and we have challenges in computing these parameters. So what we developed is this physics-guided technique that enables us, for the first time, to actually be able to deal with large data sets and account for the correlation. So how does it work? We have a non-physics model of the bridge, and we have a large number of measurements. And what we assume is that we don't know correctly what is the spatial correlation, which is the information between all of these sensors, but we want to learn it, and we want to learn it from the physics and the data. And to do so, if we do it just normally with a vanilla approach, this will take a large amount of calculation. It will not be feasible, not even for a toy bridge. And this is a real bridge that we are dealing with. So what we did was developing techniques to calculate efficiently the log likelihood, what is called the log likelihood. And for those of you that are interested in this technique, we are basically start from a physics model. We have a data generating process. And for the sampling technique, we use just standard nested sampling. And again, this was the first time that we were able to tackle this problem. And what you see there is how the physics and the data are combined together in a physics-guided framework. This was great, but we were assuming, we were making some assumption. And it was that the model prediction error was actually Gaussian. This was helping writing efficiently the way in which we can do the calculation, but there is still work to be done in that area. But this was one important challenge that we were able to solve. Another challenge is going to a different type of structures. Now we have a wind turbine that is in operating condition. This is actually real data that we had from the Western Main Park. The work was led by Joanna Zhu, and Elise Marie Lawrence from TU Delft was also the one leading this project. And we had data that come from the SCADA data that basically was giving us some information at the rotor position, but we were having also measurements along the wind turbine. So we have 3 acceleration channels that are shown here, but you can also see that we have some measurements below what is called the mud line. We were able to have access to measurement at basically the foundation, at the pole. Now, the amazing thing about this data set is that we were having data in different operating conditions of the wind turbine, but also we were having data in points in which we may have failure, normally, of the wind turbines. There are these fatigue hotspots that you see over there. So for the first time, again, by combining physics and data, we were able to validate a virtual sensing technique. What does this technique do? Basically, usually, using some of the information, just like only the accelerometer, we were able to predict what was happening below the mud line. And we were able to validate this as well. Again, this is a technique that is called virtual sensing by Gaussian process latent force model. And it's a physics encoded because we combine physics and data at the same time. And we were able to do this in situ validation. And what you see there are the steps. Now, for those of you that are interested in the step, we basically use the measurement data and we do what is called an operational modal data analysis to extract some of the information. These help us then build an identification model and combine it with the physics to look at what we don't know with the latent force model. And now we are in business, actually, to do this. There is actually predicting what is going to happen at the strain gauged position. And you see there at S2, and S2 is actually the bottom here. So we are very far away from the other information that we are using. And what you see is that we are able to predict quite accurately, actually, the strain measurements, starting from acceleration. And if you look at the paper, you will find much more information about how this was done and the work that still needs to be done. And in fact, again, another assumption that we were making to make this work is that the system is linear time invariant. Okay, now, we solve other challenges, and we were looking at other problem. And another problem is dealing with structure with friction. Every time we have a joint, you will have frictional contact. The fact that I'm walking here is also because of friction. So friction is very useful because it helps us dissipating energy, but also has some other problem. These problems are wear, noise, large oscillation. And this is what is called stick slip. If you don't know about it, don't worry. I'm going to show you a video in a second to explain to you what it is. The problem with this friction is that you may have a reduction of the remaining useful life, RUL, and you may have sudden failures. And these actually friction contacts, they are everywhere. They are in different types of structures. And you cannot actually access the contact itself. Because the contact, if you actually try to open up or put a sensor, you're basically changing the contact. So friction will change. So what you have to do is that you have to use something that leverages the data and the physics to basically look inside the contact without opening it. And we have to use what is called an integrated approach that, again, is looking at physics and data combined together. So what did we do there? So for those of you that are not familiar with friction, I'm going to just show you something that I hope is very simple. So friction is challenging for multiple reasons. The friction force is a function of the velocity and will change. And what you see there is that if the velocity is negative, you will have a certain coefficient of friction. If the velocity is positive, you will have a different value of the coefficient of friction. But now, if you look on the right, you see another figure in which there is a different law. And what you see, the difference between the two is how sharp are the edges and what is happening at the zero. Now, it's already very difficult to measure this friction contact even in laboratory conditions and to measure this frictional force. But even numerically, actually, this problem is super challenging. The reason is that we have this stick-slip phenomena that cause this sort of behavior here, in which if you see the displacement versus time, you see that there are all of these sharp variations. And what is happening is that you have motion, stop, all the time. Numerically, this is very challenging to solve. And in fact, we have to use some specialized solver, or if you use common techniques like the Runge-Kutta, we have to have some event condition to account for this different regime. Okay, I talked about a lot of stick-slip, but I haven't shown you yet what it is. And I'm going to show you a sort of simplified system that we built in the lab. This was when I was at Oxford. And what you see there is this system in which we can actually drive the base plate. And because of this motion, we will see that the top plate will move. And what you see there is a counterweight system in which by changing the position of these brass elements there, you may increase or reduce the frictional force that is applied. And what happened is that because of the disk contact with the top plate, you're going to have some frictional force that will appear. Now, I'm going to show you a video, hopefully this will work, about the motion. So what you see is first is going to be continuous motion. So you have the base plate that is moving, and the top is moving continuously. Now you're going to see stick slip in one base motion cycle. What you see there is that you can have even 4 stick slip in a motion cycle, and we can even consider 12. Now, what is interesting is that every time we have this stick slip behavior, you have also, I'm going to show you this figure, this type of very sharp edges that are appearing. If you try to apply any technique to characterize those sharp edges, it will fail. And what we did was using the state-of-the-art technique that is called Gaussian process latent force model that worked very well before for the wind turbine. And we thought, why not using it here? So we have our system, that was the one in the lab that I showed you, that can be represented as a single degrees of freedom with the mass damping stiffness. And this is the input-based motion. And what you have there is the force that you don't know. And what you can do is to say, OK, I'm going to use what is called a Gaussian process, that is a machine learning technique, to actually represent this. And if we do that, and we take the displacement, and we try to then see what is going to be the actual nonlinear force, what you see is that we are not able to capture the edges. And what we are having here when we look at the force versus velocity is that we have lots of scatters, lots of random points. And as I was mentioning to you, this problem is very challenging. And it's very challenging even if you're doing just a numerical model in forward condition. And it's very challenging if we want to collect information actually from an experiment. And now the challenge is that we want to do an inverse problem and from measurement characterize the force. And what you see is that we have the incorrect friction versus velocity relationship, especially in this part that is one of the most important, that is close to the zero velocity. So what we did there was using everything that we learned from physics. And what we did was saying, OK, wait, we have a non-physics-based model, our single degrees of freedom. We have these measurements of the output and of the input, of the base plate and of the top plate. And what we can do is to account for the fact that we know that physically we're going to be switching. We're going to be switching from sliding to sticking, but also we're going to have a resetting model. And if we combine all of this knowledge, what we have are different biases that are coming in our model and enable us to do this. For the first time, we are able to actually look at the displacement, velocity, predict the acceleration, and also predict exactly at the sharp edges what is happening at the frictional force. And you actually cannot see the 2 lines because they are overlapping over each other. And excitingly, what you see here is that automatically we can detect from the model when we are transitioning from stick slipping or resetting. And this work was led by Luca Marino. And what you see there is actually, again, the test setup and the results for the frictional force versus velocity. And now you see how we are able to predict accurately what is happening here and later on. So this was great. Again, another very nice way of combining physics and data. And this works at the moment only for one type of nonlinearity. And because we are using the Gaussian process, there are still open challenges. And again, what I'm trying to tell you is that we haven't solved all the possible problems, but combining data and physics and knowledge can help us tackle this challenge that before we could not tackle. And, sorry, I don't know what happened there. Another challenge that we have is, OK, my pointer went crazy. What can we do? Can we actually retrieve completely the governing equation? And what we are interested in is to say, let's say that you have this system in which you have the input and the output measurements, and you have high noise level. The system has lots of nonlinearity, lots of friction. And you have now a complex system, not the simple one that I was describing to you before. And what we did there was developing a technique that I'm going to tell you about. And what we are able to do, what you see there are measurements, ground truth, and our approach. What we are able to do is not just getting pretty plots, but actually getting the equation back of the problem. So this is for the first time in which we are able, for this type of system that are highly discontinuous, to go back to the governing equation. OK, so how does it work? This approach is called physics-enhanced sparse system identification. And it's a physics-encoded approach, and I'm going to tell you a bit more about this. So imagine that you have a governing question of a system that is described like the system here. And you have a part that you don't know, but a part that you know. That's a discrepancy bias, because you're adding something that you know. Now, what we can do is to say, OK, if we have these input-output measurements that vary in time, and they are even noisy, they are sparsely related, we would like to approximate this equation that we have here in this form. We're going to have, basically, some function that multiplies some coefficient, plus what we know. And what we would like to do is figure out which are these functions, right, which is this function f. And what we can do to do that is using some numerical procedure. We are going to use what we used before to solve numerical problem. There is the Runge-Kutta scheme. And we then transform this problem in an optimization problem. And basically what we're trying to do, is to look at what we say inductive biases. What are the functions that better approximate what we don't know? So we have this function f. Can we actually select a low number of functions that will be a very good candidate for representing that problem? And what we're trying to do is also to add to this problem the constraint that we know from physics, like the stick-slip condition that we know from before. And what we want to do at the end is to combine all of this together and this learning bias. And now I'm going to show you what is happening if you add all the physics, but you don't add the fact that we have stick-slip condition as an external condition. What you will get is this gray line. And again, you can see that even for this very simple system, we are missing completely off both the displacement and the velocity. But if we look at the governing equation, and we look at the ground truth equation, and what happened when we run the model with the condition embedded, we are very accurate. But if we will look into this, we will think, oh, OK, it's just a parameter, it's just a small variation. That is changing actually the physical behavior. Okay? And again, if you are able to get the true governing equation, then we can change the input. We can put different input problems and solve for different obtain different outputs. Now, the last challenge that I'm going to talk to you about is about the fact that, as I showed you at the beginning, there were two different friction laws. And if you look at the response of these different friction laws, they might actually, in some region, match exactly. What it means is that now we are looking at the mass displacement versus the forcing in all of this graph. And in some occasion, the Coulomb model and the Raytenstadt model, the DR model, are actually giving exactly the same response. And we want, again, to go back and determine the right governing equation. Can we do that? Until now, we could not. And by applying this approach, actually, if we generate data like from this, we will get, with our approach, this result. And if we generate data from a different model, then we will get this. And for all these cases, the model setup, the algorithm, is using the same dictionary of function. But now it's able to distinguish among those. So this is very efficient, and we use it also for multiple degrees of freedom and for experimental data that I'm not going to show you. And what is needed yet is uncertainty quantification, much deeper uncertainty quantification analysis. OK, so you survived this lecture in which we went through the need to go beyond data-driven techniques to what is physics-enhanced machine learning, to the challenges that we have tackled. And I'm going to describe very briefly challenges and opportunities. I hope that this is clear that these techniques may lead to accurate but wrong prediction. And because the data set can be noisy, we need, so sorry for that, challenges and opportunities relate to removing automatically inappropriate data biases, the fact that the data might be corrupted, but also assessing the quality of information. We need to have an automated way to do that. And if we think about the physics biases, I hope that this picture will help you figure out what is the problem there. Imagine that you have this solution space, and we are actually saying these are the biases to the model. And maybe the physics biases are wrong. We are now, instead of searching in the entire domain, we are looking just at this area. And we may get that type of solution. However, the correct solution is actually far away from what we found. So what this means is that we still have to work very hard on the physics and understanding the physics of the problem and try to embed as much as possible accurate physics information and removing inappropriate physics biases, if any. And physics is really enhancing machine learning and helping us doing things that we will not be able to do otherwise in engineering. And there are still many challenges and opportunities beyond what I just described to you. And of course, tackling multi-scale and multi-physics problem is one of the biggest challenges, but there are many more, including the fact that we still don't have benchmark solution, and we have problem with explainability and interpretability, and many more of this. And with this, I would like to thank you for your attention, and to tell you that the work, of course, has been supported by many grant fundings, but also by many people working very hard to provide not only the science and the paper, but also the data set and codes in open access. So if you go on this link, you will find everything you can download and you can immediately use it. And with this, I would like to really thank you for your attention. Thank you so much.
Thank you. We covered some wonderful ground. I'm going to looking around for some questions. I'm going to start. I'm a physicist, and most of the time we're extremely arrogant, but in truth we ought to be quite humble, because going back to Newton, who recognized that you can solve the laws of gravity to describe a planet going around the sun, but chuck a second planet in, you have the three-body problem. Yeah. It's not solvable accurately. So the best you can do is to run sort of real-time iterative simulations, but it's a nonlinear problem and it can blow up. And that's the easy one. Most of the time we deal with problems which have far more variables than we can ever deal with. So we just know that we're making horrible approximations and hoping we're right most of the time. So I'm sort of impressed that you think physicists can bring that sort of realism to practical models. And I try to work out, from my sense, particularly towards the end, is it that you're trying to work out what the physics models left out, where they fall down? Because to take the example of wind turbines.
Yes.
The Queen Elizabeth Prize for Engineering this year was given to, amongst others, Andrew Garrett, who set up a consultancy where they do, if you like, traditional engineering models for the physical reliability of wind turbine infrastructure. And they've done quite a good job.
Yeah,
but can you tell us what they've left out? Is that where you can...
Yeah, no, and that's the thing, there are, every time you have a wind turbine in operation, for example, you will have different operating conditions, different environmental conditions, and of course you will have degradation and things that evolve with time. And if you start from what you did at the design, you can do a brilliant design, but of course because of climate change, the loading become extreme. And what can happen is that you may have solution or condition that you haven't explored. And as a result of that, the model that you built initially is not any longer representative. So having the opportunity to combine the physics model that you had before with the data that you're collecting help you correct the model.
But the starting point is that the physics model is bound to be a horrible approximation. I mean, lots of variables will have had to be left out. Yeah.
Yeah, but that's in engineering, that's what we do most of the time as well.
Absolutely.
Horrible physics model.
Right. Let me turn it over to...
Yes, please.
I was thinking of a practical application of your techniques, particularly in the accuracy of pre-planned obsolescence of machines, or phones or domestic appliances.
Sorry, can you...
Increasing the accuracy of pre-planned obsolescent built-in.
Yes, so increasing the accuracy is one of the things that you can do, of course, with this type of technique. And the idea, again, is how you combine what you know, the domain knowledge, with the data. So collecting the data is always extremely important. but also figuring out when that data is still useful or otherwise. So there are lots of opportunities indeed in that area. Thank you.
Take a question. Yep.
Yes, please.
Thank you very much for an interesting lecture. One thing engineers tend to do is when they design things is they do all the drawings and the CAD and all the rest of it, and then they put some whacking great factors of safety, reserve factor onto the basis they don't actually know what's really going on. What we could really do with as engineers, I think, is some way of presenting all this stuff that we do know, and the bit of physics we have forgotten about or failed to include. Some piece of software needs to tell us that. But worse than that, we've got a week to do it because our boss is chasing us to find out why the thing failed.
Yes, indeed.
What's the possibility of that one day becoming a reality?
Yeah, and you're completely right that if you have a standard physics-based model or a computer software, usually it's much easier to figuring out what went wrong, what assumption you did wrong, what model, if you're using finite element, what mesh size that was used wrongly, or connection that was done wrongly. And in fact, if you then go fully on the data-driven, it's much more difficult to figure that out. And when you're combining the data and the physics, you gain something, but you end up having, again, the same problem. And yes, you fully agree with your point. Thank you.
Okay, if I may be allowed a
Yes,
question. Could we go back to your wind turbine example? Because I'd like to just understand slightly more what is actually going on there.
Yes.
Because it seems to me that we have sensors.
Yes.
There we are. We have sensors. Now, are we aware that the fatigue spot, are we deducing the presence of the fatigue spot, or are we aware that there is a fatigue spot, and then using our sensors to confirm that is a dangerous point?
Yeah.
Can you just
So
elaborate
usually when you have wind turbine, because of the loading that they are facing, the most likely failure is caused by this fatigue hotspot, basically. Right. So it's usually in this area. But most of the time it's very difficult to monitor that area. So it's much easier on all the wind turbines to actually go and stick some accelerometers along the tower of the wind turbine. Right. And because of that, usually we have access to information at the top or at the, basically, at this part, here, in this part, or here. And what we were trying to do was develop this virtual sensing technique. That what it's saying basically is that even if you have just these three measurements, now because you're combining physics with data, you're able actually to have measurements virtually everywhere. And
so
now we can measure even
you're
that.
using the red sensors
exactly.
to predict what is happening where you would have the green sensors.
Exactly. So this is the measurement data, and we use this as validation data.
But when you say validation data, does that mean in this case that you do have green sensors there, or are they virtual sensors?
For this very unique case, we have those measurements.
Right.
And so we are using then the virtual sensor, and we are validating with real data. And this is actually what was shown here, in which basically we have the real data versus what is modeled. So the true and what we are estimating.
So in other words, okay, I've got it. So in future, we can just use the red data.
Exactly.
And we can deduce when we have a
everywhere else where we
Okay,
need.
good.
Thank you. Thank you for your question.
I understood that bit.
For the clarification.
Thank you. I know it's outside your field, but when you had that sentence up about models which produce accurate predictions which are entirely false, what immediately came into my mind was treasury economic models. And I wondered whether you thought that your approach had any applicability there.
It's actually very much outside my field, so thank you.
I have a question, if I may, Alicia. When you were talking about the wind turbines and the bridges, I was thinking about one of the most famous engineering failures, which is the Tacoma Narrows suspension bridge.
Yes.
Where it was nicely designed and it bore all the trucks and such like, but there was a high Q resonance in the structure with a certain wind speed, and it blew over, basically. It collapsed. Do you think you could build a physics-enhanced model that would see it just coming up to resonance and then the wind dying away and it stopping, and thereby, they wouldn't have had strain gauges on the bridge at that time, but for future bridges, to identify these bits of unknown, high Q is the particular problem there, unknown factors, and identify them as problems. Actually, a more modern version is the bridge over the Thames, the pedestrian bridge over the Thames.
It had a bit of a wobble, didn't it?
The wobbling.
Yes.
Millennium Bridge. Yes, and indeed, that's exactly the point. So you're collecting the information over time, and you are looking for evidence that things are changing, and the system is varying. And you're looking for conditions that might lead to failure. What it means by that is that if you are now having data and you are updating your model, you can run the model in forward analysis and making prediction. And that prediction can tell you how much of the remaining useful life for that structure is there, or if you are in a dangerous zone, basically. And then you can decide if having predictive maintenance, if you want to have maintenance or you want to stop the bridge, or if you want to have an inspection, basically. So someone going there and do the checks. But yeah, it combines basically the information from the wind, from satellite, from strain gauges, and other information.
But you'd have to have real-time monitoring.
Exactly, and that's the challenge.
So that was the sort of, the parallel to this huge capacity to assimilate vast amounts of data is that we can have vast amounts of data, and the opportunities to do much more measurement on large physical structures have changed remarkably.
Yeah.
It's part of the opportunity to work out what, where and what should be measured.
Exactly, and that's exactly the problem. We can have large amount of data, but they might not be informative. And understanding where and what is becoming one of the biggest challenges as well that we are facing now, especially for doing live decision making.
Great. I think we should probably call a halt. It's a fantastic lecture. A lot to, it's been stretching my physics brain quite a lot, actually. Or what's left of it. But thank you so much. It was a wonderful lecture. Thanks so much for coming out this evening.
Thank you. Thank you so much.